Hello everyone, and welcome back to another elementary stats lesson. In this lesson, we're going to continue our conversation in Chapter 7 on hypothesis testing. And the important thing that we're going to do today is we're going to fill in the gap from the last lesson, where we introduced the notion of a hypothesis test, but there was a conspicuous point where we said, and then you find a standardized test statistic, and then you compute an area and to get your p-value. And we didn't really specify how you do that. Well, this lesson is going to tackle that question. And the reason we left it a little murky last time was because how you calculate it is very dependent on the setting. For example, here you'll notice in the title of this section, sigma, the population standard deviation, is a known quantity for us. This is different than, say, sigma being unknown, or instead of testing for the mean, maybe you'd be testing for a population proportion. So depending on what setting you're in, that step of converting to a standardized test statistic is going to be a little different. We'll see what we mean about that in a moment. To begin with, let's recall some facts. In Chapter 5, we will remember that as it related to the central limit theorem, we learned that when the sample size is at least 30, the sampling distribution for x bar, the sample mean, is normally distributed. Additionally, there's another background option, which is if your original distribution is already normally distributed, then your sampling distribution for the sample mean is also normal. We recall that, as we mentioned in section 7.1, we learned what p-values were and how we can use them to conclude things from a hypothesis test. And we might remember some of those conclusions. We note that when we assume the null hypothesis is true, then the p-value that we're going to figure out how to compute is the probability of obtaining a sample statistic with a value as extreme or more extreme than the one determined in the sample data. And in particular, if the probability of obtaining such a sample statistic is very, very, very low, then what that means is that the sample that you ended up picking is maybe conspicuous and kind of broken in some capacity, but what that means is that your underlying hypotheses that you're using to generate this sample statistic must be faulty, and the only hypothesis that you're assuming is the null hypothesis, and hence you reject the null hypothesis. Compacted, what this means is the following decision rule that we're recalling. In particular, we choose some sort of an alpha, which is our significance level, and we say that if our p-value is less than or equal to alpha, we're going to reject the null hypothesis, and if our p-value is greater than alpha, then we will fail to reject the null hypothesis. Again, we make a note here that failing to reject the null hypothesis does not mean you necessarily accept that the null hypothesis is impossible. It just means that there is insufficient evidence. So to quickly test and make sure that we understand how all these math values are running around, suppose you're given a hypothesis test and you achieve a p-value of 0.0237. Depending on what your level of significance is, you may or may not choose to then reject the null hypothesis. For example, maybe you're okay with your level of significance being 5%. And in this case, half a percent. And in this case, since your p-value 0.037237 is indeed less than 0.05, our conclusion is that we're going to reject the null hypothesis. But, for example, if instead we had something like a 1% level of significance, like so, then what we'd observe is that that same p-value that we might conclude from our hypothesis test, 0.0237, is now greater than our level of significance, 0.01. So the conclusion is that we fail to reject the null hypothesis. Depending on the context, you get to choose, or the problem will tell you what your level of significance is. Oftentimes, if the stakes are higher, your level of significance is lower. So, for example, if the conclusion of your statistical study literally puts human lives in the balance, you might want to make really sure that if you're going to reject the null hypothesis, that you're very confident. And so you're going to set your alpha, your level of significance, to be very low, maybe, for example, 1%. Whereas if it's less consequential, if you make a type 1 error, that is, if you end up rejecting a null hypothesis that was actually true, then maybe your significance level can be a little bit higher, like, say, 5%. Now, how do we actually find these p-values? That's the question we're here to answer. The way it's going to work is that, given the situation you run into, you are going to end up taking a sample. When you take that sample, in this section, we're going to talk about then taking sample means. Once you get that sample mean, you're going to want to convert it to a standardized test statistic, which for us is going to be a z-score in this section. And then you're going to draft up a normal curve, a little bell curve, and you're going to find some sort of a corresponding area. The corresponding area depends on the nature of the test, meaning either a left tail, a right tail, or a two-tail test, where the p-value is going to be the area either in the left tail, the right tail, or split, where half the p-value is found in each of the left and the right tail. So let's take a look at an example of what we mean by utilizing these tails to find p-scores, p-values. So here we want to find a p-value where we have as an assumption that we're working with a left-tailed hypothesis test, and we've already converted to a standardized test statistic, in this case a z-score of negative 2.23. So what this means is, since it is a left-tailed hypothesis test, I know that I'm going to draw a picture of a normal curve where z here is 0, and z equals negative 2.23 is over here. This is a z-axis, and so we end up with that curve. And notably, this area in here is exactly, since we're working with a left-tailed test, this area in here is going to be exactly the area in question. So the area of this is going to be our p-value p. So we ask ourselves, how, if you're working with a standard normal distribution, if you know of a z-score, how do you compute the area to the left of that z-score? Well, we actually already know how to do that. We've done this plenty of times so far in this semester, right? What you use is you use the standard normal table. What you do is you look for the z-score of negative 2.23, and that'll tell you the corresponding area to the left of that score. So use the standard normal table. So we'll say, using the standard normal table, the area to the left of z equals negative 2.23 is, now in the past I actually went down to the normal table and showed us how to go through this process, but at this point we've done this so many times, I'm simply going to state the values, and you're encouraged at home to confirm for yourself by looking at the table that indeed this is the value we should be getting. And in this case, the desired area is 0.0129. So that's going to be my p-value. This is my p-value. So what can we conclude? Since the p-value, which is 0.0129, is greater than the level of significance 0.01, the conclusion is that we fail to reject the null hypothesis. So this is what it looks like when we have a left-tailed test. Instead, we might have a two-tailed test. And in this case, we have a standard test statistic of positive 2.14. So I'm going to start in exactly the same way. I'm going to draw my normal distribution. Here's a 0. Now the two-tailed test means that there's going to be some sort of a cutoff point to the left and then to the right, where my p-value is going to be the sum of the areas over here in the left tail as well as the area over here in the right tail. So we'll note that. So our p-value is the sum of these areas. But these areas are the same, so it's really just twice this area of one of them. So the given standard statistic is 2.14, so positive, that's going to be over here on the right, that's 2.14. The value on the left, the critical value to the left, is also going to be not 2.14, but negative 2.14. And since the standard normal table returns areas to the left of a given statistic, what I'm going to do is compute this area over on the left using the table, and then simply double it to account for the other tail, and that'll give me my p-value. So what we'll say is that using the standard normal table, which again, you have access to, the area to the left of z equals negative 2.14 is 0.0162. You can verify that at home. So my p-value is not going to be that value because this is not a left-tailed test. It's a two-tailed test. So it's going to be twice that quantity, 0.0162. And if we multiply that by 2, we get 0.0324. That's going to be our p-value. And so in this two-tailed instance, we find that since the p-value, 0.0324, is, well, now we compare it to the level of significance given to us, which is different from the previous problem. And in this case, we find that it is actually less than the level of significance, 0.05. Our conclusion is that we do, in fact, reject the null hypothesis. Now, of course, these two examples help us understand how to compute p-values once we're given the test statistic z. How do we get that test statistic? Well, it's a simple matter of taking whatever the sample statistic is that you were given and then converting it into a z-score. We've seen this in the past. In particular, for this section, if sigma is known, then we're going to use a z-distribution, and we can convert our test statistic x bar into a z-score via this computation. It's going to simply be x bar minus the hypothesized population mean mu all over the standard error, which we might recall is sigma over the square root of the sample size. So we're starting to put all the pieces together. So this z-score computation we have here, we're going to call the standardized test statistic. And what we're going to call this is the z-test for the mean. This is a statistical test for, in particular, the population mean. And the test statistic that we're utilizing for this is the sample mean x bar, and then the converted z-score is given on as we gave on the previous page. Now, of course, the underlying assumptions for this, much like they were in Chapter 6, are making sure that the central limit theorem applies. So in particular, the sample is random, and we need one of two things to be true. We need either the population to be normally distributed, or the sample size is sufficiently large. It might be worth noting that the sample mean can otherwise be written as sigma sub x bar. So you might want to keep that in mind in case we pass back and forth between those. But now what we're set up for is we're set up for tying it all together. We've done a lot of different pieces. We've talked about how to develop a null and an alternate hypothesis. We've talked about how to conclude things if you're given a p-value. And we just talked about how to find a p-value from a given standardized z-score. And what we have here now in front of us is how to convert a sample stat into a z-score. So we have there's a lot of moving pieces going on, and we've talked about each piece individually. What we want to do now is sew it all together and build a giant master plan. And that's what this is. This is going to be using p-values for a z-test for a mean mu where sigma is unknown. Known, sorry. This is an important part here because if sigma is unknown, we cannot use a z-distribution, and we'll talk about that in the next section. But this is the process. Step 1, verify that sigma is known, the sample is random, and either the population is normally distributed or you have a sufficiently large sample size. Step 2, interpret your words in math. Identify the null and alternative hypothesis. Step 3, specify your level of significance that you're going to compare your p-value to. Step 4, convert your test statistic into the standardized test statistic by computing its z-score. Then we're going to, once we have the z-score, use the standard normal table to find the area corresponding to that z-score. That area is either going to give us our p-value or inform us on how to find our p-value. In particular, we have a lot of these sub-rules for depending on whether we are using a left, right, or two-tailed test. You might recall that the nature of the test that we use is completely dependent on how the alternate hypothesis is written. We'll see an example of that in a bit. Once you have your p-value, then you compare it to your level of significance and you conclude whether you reject or fail to reject the null hypothesis. And then finally, based on whether you rejected the null hypothesis or not, you can then interpret what happened within the context of the original claim. This 8-step process is what we're going to follow in order to make any sort of sense out of real-life applications of this process. It's a little complicated, but once you do it a few times, it starts to make a little bit more sense. That said, let's take a look at an example so you can see how I would write this, and you can see what sort of steps and what moves one has to make along the way. So here's a real-life example. In auto racing, for example, NASCAR, Formula One, things like that, there's a thing called a pit stop. A pit stop is where the vehicle stops and essentially the team performs some kind of maintenance. Usually it's 4 new tires and some fuel. The efficiency of a pit crew is super important. If these cars are going upwards to 200 miles an hour, then if you stop for, say, 15 seconds, that's probably the better part of like a quarter to half a mile that all the other cars get on top of you. So you want to minimize your pit stops, the amount of time it takes. So a particular pit crew claims, and as soon as we read the word claim, we're hyper-vigilant. They claim that its mean pit stop time is less than 13 seconds. Okay? You say, oh, maybe that's true. I don't know, we'll see. You take a random sample of 32 pit stop times that they have, and you compute a sample mean of 12.9 seconds. You assume that the population standard deviation is 0.19 seconds. So you know the standard deviation, that's important. And so now you want to see whether there's enough evidence to support the claim using a p-value and comparing it to a level of significance of 1%. Well, for starters, again, the way I'm going to write this is I'm going to follow this 8-step process. So for starters, we're going to verify some information. What we see based on what was written so far is that since sigma, this population standard deviation, is known, and additionally, the sample is random. That was told to us right here. And the sample size given is 32, which notably is greater than or equal to 30, so it's sufficiently large. This tells us that we can use the z-test. What that means for us is we're in the context of section 7.2 and no other section. Now, what we're going to do is we're going to write down the claim because we need to convert this into a null and an alternate hypothesis. The claim was given to us as the mean pit stop time is less than 13 seconds. So the claim is that the mean is less than 13 seconds. So we need to convert this into a null hypothesis and an alternate hypothesis. Remember, however, that the null hypothesis always contains the equal sign. There's no equal sign in the claim, so that means that the claim cannot be the null hypothesis. The claim must be the alternate hypothesis. The opposite of mu being less than 13 is mu being greater than or equal to 13. So these are our null and alternate hypothesis where the claim is representing the alternate hypothesis. At this point, we're going to start computing p-values. So we want to remind ourselves that the level of significance is 1% because alpha is 0.01. So once we know what to compare our p-value to, we're now going to find our p-value. The first step to finding our p-value is to find the standardized test statistic for our sample mean. So the standardized test statistic for our sample mean x bar being 12.9 is, well, now we're going to use our formula for converting this to a z-score. Z is going to be, remember the formula is x bar minus mu over the standard error, sigma over square root of n. So in this case, we're going to get 12.9 minus the proposed mu, which was 13. Because again, we're assuming that the equality in the null hypothesis is valid. That's the whole point of all of this. And we're going to divide that by sigma, which was given to us as 0.19, over the square root of the sample size 32, and this is going to be, after rounding to 2 decimal places, approximately negative 2.98. So now that we have our standardized test statistic, we need to now compute some areas using the standard normal table, but we also need to be clear on whether we are a left, right, or two-tailed test. But since the alternate hypothesis here is a strictly less than symbol in it, that means that we're going to be using a left-tailed test. Since h sub a has mu less than 13, the important thing is the less than symbol there. This is a left-tailed test. So in particular, the area that we're looking for to compute our p-value, here's the normal curve, that's 0, this is a z-axis. We're going to have some sort of a z statistic here, which is negative 2.98, and then the area to the left of this test statistic over here, this is exactly the area that gives us our p-value. So the area here is equal to our p-value, but by the standard normal table, the area to the left of the z-score negative 2.98 is exactly, and you can confirm this at home, 0.0014. So because we're a left-tailed test, this is our p-value. Now comes the question of, since we have our p-value, we compare it to our level of significance, and we say that since our p-value, which is 0.0014, is in fact less than the level of significance 0.01, the conclusion is that we reject the null hypothesis H0. That is, we reject that the mu is greater than or equal to 13. All of this math is great and all, however, at the end of the day, the question was posed in a real-life word paragraph sentence that you could, posit to real people, and so our conclusion needs to also be written in words. The conclusion of we reject H naught is not helpful to almost anybody. We need to interpret that. So we need to provide some sort of a conclusion, and we might say the following. Since we rejected H naught, the conclusion would be something like, we found that there is enough evidence, not just enough evidence in general, but in particular at the 1% level of significance to support the claim, because remember, if we rejected H naught, our claim was the alternate hypothesis. So if we've rejected H naught, what that means is that we have enough evidence to support the alternate hypothesis, which in this case was our claim. So in this case, we have enough evidence at the 1% level of significance to support the claim that, and now we write out what the claim was. In particular, the mean pit stop time is less than 13 seconds. And that concludes the problem here. This 8-step process is a little long and admittedly somewhat tedious, but this is how we can start with a real-life scenario with real-life data, and we can slowly but surely put together everything we've been learning in this 8-step process to essentially mathematize all of the English, perform some statistical analysis, and then yield a conclusion at the end. This right here is sort of what we've been building up to this entire time. And this is where things start getting really, really useful in the real world. So we're going to pause here for the first video, and we're going to resume the next video, taking a look at the next page of the handout as we continue this conversation.